Let's go to question number 3. You have the extension y of a given material is a function of f given by this function e to the power of f times 10 minus 2 times this decimal. The first question is to calculate the work done if the force increases from 100 newtons to 500 newtons using an analytical integration method for the first part. For the second part, a numerical integration technique. B, compare the two answers. C, using a computer spreadsheet, increase the number of values used for your numerical method. This will give you some hints on how to do, because I'm not going to do it here. And I will explain about D, what needs to be done for part D. So for the first, the analytical technique, we just have to calculate the integral. The work is going to be the area under the curve, so it's going to be 100 to 500 of e to the power of f times 10 minus 2 df is going to be this integral. That is going to be e to the power of f times 10 minus 2, and to balance you divide by 10 minus 2. So that's going to be 100 times e to the power of 500 times 10 minus 2 minus e to the power of 100 times 10 minus 2. So that's going to be e to the power of 5 minus e to the power of 1. I'm not doing anything special. I have this definite integral. I find the function, then I have to evaluate the function at this at the top value minus the evaluation of the function at the bottom value. What is e to the power of 5 is going to be roughly 2.71 to the power of 5 minus 2.71, okay, just an approximation. 2.71 raised to the power of 5, that gives me 146 roughly, 146 minus 2.71, these very ugly numbers. So that's gonna be 100 times 143.29. If I'm not mistaken somewhere. So that's gonna be 14329 joules. So this is the work done. Is going to be this value. And now we proceed with a numerical approximation. We will use the trapezoidal rule for number 2. Okay, my function, it looks like this. So that is f, and that's y of f. Now if I start from 100, is going to be for f equals 100, y is going to be e to the power of 100 times 10 minus 2. That's going to be just e. I want to integrate numerically from 100 to 500. So let's imagine that that e to the first power is somewhere here, and then for f equals 500, we have y equals e to the power of 500 times 10 minus 2. That's e to the fifth power. So let's say that it's somewhere like here. The trapezoidal rule says the following. Let's find the step size. H is going to be b minus a over n, 500 minus 100 over, and n is the number of trapezia I want to use. I want to use 4 in this case. Let's say we want to use 4 trapezia. 400 over 4, that's gonna be 100. So it's 200, 300, 400. I have one trapezium here, one trapezium here, one here, and one here. Okay? So I have the area of the first trapezium, the area of the second, the area of the third, the area of the fourth. I need to find these slices. So A1 is going to be the small base. This one is going to be y evaluated at 100 plus the big base is y evaluated at 200 times the height, which is this slice, times 100 over 2. So A1 is going to be 50 times y 100 plus y 200. That's going to be the area A1. A2 is going to be the small base plus the big base, so it's going to be y 200 plus y 300 times by the height, which is 100, the height is this slice here, over 2. So A2 is going to be 50 y 200 plus y 300. That's gonna be A2. A3 is going to be y 300 plus y 400 times by the height, which is 100, divided by 2. So the formula for area A3 is going to be 50 y 300 plus y 400, and for A4 is going to be y 400 plus y 500 over 2 times the height, which is 100. So A4 is going to be 50 times y 400 plus y 500. You calculate each one of these. Okay, you have to calculate each one of these. So A1 is going to be 50 y100 plus y200 is going to be 50e for the first power plus e to the power of 2. a2 is going to be 50 y200 plus y300, 50 times e to the power of 2 plus e to the power of 3. a3 is going to be 50 y300 plus y400. That's going to be 50 times e to the power of 3 plus e to the power of 4. And a4 is going to be 50 y400 plus y500. E to the power of 4 plus e to the power of 5. So let's find a1. 50 times 2.71 plus 2.71 squared. .71 plus 7.3441 2.71 plus 7. This stupid calculator. It's gonna be 50 times 10.05. 50 times 10.05. It's gonna be 502.5. a2 is going to be 50 times 2.71 raised to the power of 2 plus 2.71 raised to the power of 3 . So that's going to be times 27.2. 50 times 27.2. That's going to be 1360. And for a3 is going to be 50 times e to the power of 3 plus e to the power of 4. 2.71 raised to the power of 3, 19.9 plus 2.71 raised to the power of 4, 53.9. Okay, let's round it up. 50 times 20 plus 54. That's going to be 50 times 74. 50 times 74, that's going to be 3,700. And then for a4 is going to be 50 times e to the power of 4 plus e to the power of 5 e to the power of 4, 2.71 raised to the 4th power. It's going to be 54 plus 2.71 raised to the 5th power is going to be 146. It's going to be 50 plus 50 times times 200. is 10,000. And now we have to add all them up. A1 plus A2 plus A3 plus A4. You add them all up. So you have 503 plus 1360 plus 3700 plus 10,000. That's going to be 15,563. And the original result was 14,329. So the analytical, it was 14,329 joules, and the numerical 15,563. Now we compare the two answers. They are good approximation, so we get good approximation. Because the values are close to each other. Now for C, you can use Desmos. Type trapezoidal rule. And this will give you the opportunity to do this using a software. I think it's more easy and less painful than doing all these computations. And the last one, if you increase the step, it means that you use more trapezia, so the approximation becomes better. Smaller step size gives better approximation using a numerical integration scheme. Okay, that is the end of this part of the video.